Hello, I'm Joseph Kasser, and welcome to this podcast where the AI team does a deep dive into some application of systems thinking.
Welcome to the deep dive. Today, we're going to be looking at systems engineering. We're using this paper by Joseph Kasser, and I think we're going to learn some really interesting stuff.
Yeah, definitely. There's way more to it than you might think. It's more than just, putting pieces together.
Right, and that's what we're going to be talking about, emergent properties.
Yeah.
Sounds kind of mysterious.
Yeah.
And to make it even more concrete, we're going to be using the Widget Project, which is a hypothetical example from the paper.
The Widget Project is great because you get to see all these ideas actually play out. This seemingly simple project that uncovers all of these really tricky problems.
Okay, so before we even get to the widget, can you give us just a simple definition of what a system is? I mean, it sounds basic, but I have a feeling it's more complicated than it sounds.
You're right. It is more complicated. And that's a great question because it's really the foundation of everything we're going to be talking about. But in simple terms, a system is just a bunch of parts that interact to do something. And each part is like a mini system on its own, often called a subsystem.
So like the engine in a car is a subsystem, but it's also made of parts that form even more mini-systems.
Exactly. And the key is when you put all these subsystems together, when they interact, they create properties that you wouldn't expect just by looking at the parts individually. It's kind of like if you're baking a cake. You've got all these ingredients, but it's only through the process of mixing them and baking them that you get the flavor, the texture, and the overall experience of eating a cake. Those are what we call emergent properties.
Oh, okay. So the cake itself is like the system. The taste is like an emergent property.
Exactly. Now, just like with cakes, emergent properties can be good or bad.
Yeah.
So some are desirable, like that deliciousness of the cake, but some are undesirable, like if your cake burns or sinks in the middle. And these are the unexpected problems that engineers have to deal with.
Right. I can imagine those undesirable properties causing some real headaches in a big engineering project.
Absolutely. And to make it even more interesting, you sometimes get serendipitous emergent properties. So these are unexpected benefits, like if you accidentally discovered a new flavor combination while baking. But to manage all of this, engineers have a roadmap, and that's the system life cycle.
Okay, so tell me about that. Is it kind of like a checklist that they follow?
Yeah, you can think of it like a series of stages. And it's often visualized as a waterfall, so each stage kind of flows into the next one. Starts with what we call needs identification, which is just figuring out what this system is actually supposed to do. Then you move to requirements, which is getting very specific about what that system needs to be able to achieve.
Okay.
And then there's design, where you're creating the blueprints, so to speak.
So far, that sounds pretty straightforward, but I bet it doesn't always go that smoothly in reality, right?
Yeah, you're right. Just like in life, there are often detours. So in systems engineering, we call these abnormal exits. It's like if you had to rewrite your cake recipe midway through because you forgot an ingredient.
Right.
These unforeseen problems can force you to go back to earlier stages in the process.
You have to be able to adapt and adjust as you go, which makes sense. Now, when you're going through all these stages, is it all about finding the right answer? Or is it, I don't know.
Well, it's more about solving one problem only to discover a new one. So each stage kind of has a what and a how. The what is the problem and the how is the solution. And what's fascinating is that the how of one stage often becomes the what of the next stage.
Okay, can you give me an example?
Sure. So let's say you've figured out the requirements for your system, and that's the solution to the problem of defining what it needs to do.
Right.
But now those very requirements become the problem for the designers,
Yeah,
who have to figure out how to build a system that meets all of those specifications.
I see. So the solution to one challenge becomes kind of sets up the next one.
Yeah, it's a chain reaction of problem solving. And that brings us to our case study, the Widget Project.
Okay, let's hear about the widget.
Yeah.
What kind of system is it?
So imagine you're an engineer at this company called Federated Aerospace, and your task is to develop this new system called the Widget. Sounds simple enough, right? It just involves connecting two subsystems. So the team decides, mechanical fastening method is the way to go. Keep the costs down. They're going to use commercially available, off-the-shelf fasteners.
Okay, so something like nuts and bolts.
Exactly. A simple nut and bolt to hold those subsystems together.
Well, that sounds pretty straightforward. What could possibly go wrong with something as basic as a nut and bolt?
Well, that's what the team thought, too. But that's where it gets interesting. They thought they had a simple solution. But the Widget Project is about to teach them some valuable lessons about the unexpected complexities of systems engineering.
This is where those emergent properties come in.
Yeah, got it. But we'll save that part of the story for next time.
So we're back and ready to hear what happens next with the Widget project. Last time we left off, our engineers thought they had it all figured out with that simple nut and bolt, right?
Right. They cruised through those initial phases.
Yeah.
They built the subsystems, they tested them individually, even put the whole system together. Everything seemed like it was working perfectly.
So what happened? Where did things go wrong?
Well, they get to this crucial system test phase, and this is where they make sure the whole system actually functions as intended in a real-world kind of environment. And that's when they discovered this big problem.
What happened? Did the nut and bolt just fail?
Yeah, under certain conditions, specifically vibration.
Okay.
The nut and bolt would come loose and eventually separate. So they had this big, undesirable emergent property.
Wow, that's kind of surprising. I guess you can't always predict how things are going to behave, when they're all put together, especially in a brand new system like this one.
Exactly. And that's a key lesson here. Even the simplest components, can lead to complex problems. What's interesting is, the system worked perfectly fine as long as there was no vibration. But once they started simulating those real-world conditions, that's when the trouble started.
So what do they do about this setback? Did they just scrap the whole thing?
Not at all. They took it as an opportunity to learn and adapt. Remember those abnormal exits we talked about? This is a perfect example. They had to go all the way back to that needs identification stage and reevaluate their whole approach.
Okay, so instead of going forward, they had to kind of take a step back. I bet that added a lot of time and cost to the project.
Oh, absolutely. Delays and budget overruns are very common when you run into these unexpected problems. But good systems engineers, they're problem solvers, So they dug deep and tried to figure out exactly why this nut and bolt was failing.
How did they do that? Did they just, I don't know, tighten the bolt more?
It was more complicated than that. They had to conduct a bunch of tests to figure out what level of vibration was causing this failure. It turns out there was a specific threshold. Beyond that, the nut and bolt just couldn't hold up.
Okay, so it wasn't just any vibration, but a certain amount that would cause the problem. That's interesting. So once they knew that, did they just, redesign the whole fastening system?
Well, they considered different options, but they came up with a pretty clever solution.
Okay.
They decided to add a star washer to the design.
Okay, so I'm not an engineer. What's a star washer?
It's a small but mighty component. So it's got these teeth on it, and they dig into both the nut and the surface it's attached to, creating more friction, and that prevents the nut from loosening under vibration.
Wow, so just that one little addition fixed the whole problem. That's amazing.
Yeah, it really shows how important attention to detail is. But adding this star washer brought up another question. Where should they put it within the system? Should it be part of one of the existing subsystems, or should it be its own separate subsystem?
So this is where, subsystem boundaries come into play, right?
Exactly. And this is where the team had to make a strategic choice. Should they create this whole new subsystem just for this star washer, or should they incorporate it into an existing one?
What did they decide?
They decided to include the star washer within that the nut and bolt subsystem, and just rename it the fastening subsystem.
Okay.
And this shows how these system and subsystem boundaries can really shift. As you learn more about how the system behaves, you might make some design changes. It's not always set in stone.
Yeah, this project's really showing us how dynamic this whole process can be. I'm curious to know, what other lessons do the engineers learn from all this?
Well, one key takeaway is that unknown emergent properties, they can pop up at any stage, You can plan and you can test as much as you want. But there will always be those surprises, especially in a first-of-a-kind project like this one.
So you have to kind of be prepared to expect the unexpected. It sounds like adaptability is just as important as technical skill.
Absolutely. And the widget project shows us that, sometimes these seemingly minor design changes, like adding that star washer, can have a huge impact on solving those major problems. Sometimes it's those little details that make all the difference.
That's a great point. Okay, so we've seen how this, pretty simple project got really complicated really fast. Before we wrap things up, can you just summarize, the key takeaways from the widget's kind of journey?
Okay, so the widget project taught us that system and subsystem boundaries can change. Unknown properties can emerge at any time. Seemingly small changes can have a big impact. And planning for iterations, those unexpected delays, is crucial.
So it sounds like to be a systems engineer, you have to be part detective, part inventor, and very, very patient.
Well said. Systems engineering is this constant dance between solving problems and uncovering new ones. You have to be comfortable with ambiguity and just embrace that iterative nature of the process.
Okay, I'm starting to understand why this field is so important. Now, before we wrap up this deep dive, I have a question for our listeners to think about. And it's inspired by that, little but mighty Star Washer. Think about the everyday objects you use, your phone, your car, even your coffee maker. What are some seemingly minor components that play this huge role? And what would happen if they failed? It's amazing how much we rely on these complex systems without even really thinking about it.
That's a great point. It makes us appreciate all that complexity, hidden beneath the surface, all these things that we take for granted.
Right, exactly. So deep divers, take a moment to look around you. Marvel at all those intricate systems that make our modern world possible. And, next time you see a nut and bolt, don't underestimate its potential for both, triumph and trouble. Thanks for joining us. Okay, so we've seen with this widget project how something so simple, like using a nut and bolt, can reveal a lot about systems engineering.
Yeah, it shows how even the tiniest parts can have like a domino effect on the whole system.
Yeah, and sometimes those effects don't even show up until, pretty late in the process, like that whole vibration issue.
Right. Which brings us to a really important point. Those emergent properties, the ones you don't expect, those can really mess things up.
Yeah.
It's like you think you've got it all figured out, and then, bam, you get to the testing phase, and something totally unexpected happens.
That's when you have to make one of those abnormal exits, right? Like having to go back and change your cake recipe in the middle of baking.
Exactly. Can be super frustrating. But it's so important to be able to, adapt and iterate. You just can't always predict every challenge that's going to come up, especially when you're working on something that's never been done before.
Speaking of adapting, I was thinking about how the team, just changed the name of that subsystem from nut and bolt to fastening subsystem just because they added a Star Washer.
Yeah, that's a great example of how those boundaries between systems and subsystems can change over time. It's not always like super clear from the start. Sometimes you have to shift things around as you learn more about how the system actually works.
It really shows that systems engineering is a lot more, dynamic than people might think.
Oh yeah, for sure. It's about really understanding how all the parts work together and being able to change your approach when you learn something new.
So before we wrap up our deep dive today, can you give us just the main takeaways from the widget project? What are the most important things you want people to remember?
Okay, so the widget project taught us system and subsystem boundaries can change, unknown properties can emerge at any time, seemingly small changes can solve major problems, and planning for iterations and unexpected delays is super important.
It seems like to be a good systems engineer, you have to be flexible and willing to, learn from mistakes.
Yeah, absolutely. It's not just about knowing all the technical stuff. It's also about being able to solve problems, working well with others, and being really curious.
I think the Widget Project did a great job of showing all that. It really opened my eyes to how complex these systems are, even the ones that seem really simple at first.
Definitely. It makes you wonder, what other problems are hiding in all the systems we use every day, right?
That's a great question for our listeners to think about. So everyone, think about it. Your smartphone, your car, the appliances in your kitchen, all those things. What tiny little parts are in there? And what would happen if those tiny parts broke?
It's kind of a reminder that those little things can have a big impact, and also that systems engineering is all around us, working behind the scenes to make our lives possible.
So true. Thanks for joining us today on The Deep Dive. Hopefully you've learned something new about how these amazing systems work and all the challenges that engineers face when they're designing them. See you next time.